Dear friends, in the last lecture we discussed what is known as fan total pressure. Fan total pressure helps us to select a fan, and what are the fans used in HVAC system is the objective of this lecture. Well, there are many types of fans available in the market, but primarily it is the centrifugal fans which are used in the HVAC system. So this lecture would concentrate on the centrifugal fans used in HVAC. So what is a centrifugal fan? Centrifugal, the term itself helps us to understand what a centrifugal fan means. It has to do with the direction of the flow as to how the air enters the impeller. So in the centrifugal fan, as you see in this figure, in the HVAC system, the air would enter in the axial direction. Okay, so you see over here, air is entering in an axial direction and it is propelled outside from the outer circumference of the fan. Okay, so you see that air enters a centrifugal fan axially. It then turns and moves in an approximate radial direction into the blades, and then the air leaves the blades. It enters the scroll. This is called as the housing, which channels the air around the periphery of the wheel, and then it directs it towards the outlet. Okay, so this is the way the centrifugal fan operates. This fan may have a single inlet or it might have a double inlet, depending upon whether the air enters the impeller from one side or from both the sides. So this figure is the one which shows a single inlet. As I said, the usual direction of discharge is horizontal, but in certain applications the discharge could also be non-horizontal. Let us now discuss a bit about the types of centrifugal fans. Primarily, there are four types of blades used in centrifugal fans. One is the forward curved vane type of fan. The other is called as the backward curved. Third is the radial type, and fourth is, it is not listed over here, it is called as a airfoil type. So the one which is commonly used of these four is the forward curved blade. Okay, so the forward curved blade is commonly used in our air conditioning systems, which is usually the low pressure air conditioning system. And there are other types, as I said. For example, the backward curved blade fan and the airfoil type of blade fans, they are used in high volume or high pressure systems where increased efficiency is important. Okay, so we would be discussing mostly the forward curved vane fan and compare it with the backward curved vane fan. Okay, so as I said, the main objective is to discuss the forward curved vane fan in comparison with the backward curved vane fan. Why is that so? That is because this type, that is a forward curved vane fan, is commonly used. So these pictures, they show these three prominent types centrifugal fans. This one is the forward curved. You see this blade tip. This tip is in the forward direction as compared to the direction of rotation. This tip is backward as compared to the direction of rotation, and this is radial. Okay, so this is how they are defined. So as I said, these beautiful pictures, they are the pictures of forward curved fans. Okay, so these figures, they show you the blades. The blades are fixed in a way that the tip of the blade, they are tilting towards the direction of rotation. Okay, forward curved impeller, this is called as impeller. This is the impeller. It requires a housing. This is called as housing or a scroll. Okay, that converts the high velocity air, leaving the tips of the blade into the low velocity static force. So the job of the housing is to convert the high velocity air into the low velocity air by partial conversion of it into a static force. Okay, and this shape is very important. The shape of the housing is important. It also directs the airflow to the outlet. So that is how the forward curved planes are characterized. One of the important way of distinguishing or identifying a forward curved centrifugal fan is its cylindrical shape, and there are a lot many small blades on the circumference of the impeller. Okay, so if you look at this kind of structure, then you can easily identify that this has to be a forward curved centrifugal fan. Now, what is seen over here now is what is known as the performance curve of the fan. Okay, so the performance curve of the fan, it shows you how the static pressure, this is the static pressure, this curved thing is the static pressure, how it changes with the respect to the flow rate. Okay, so how the static pressure changes with the flow rate. If you look at this kind of typical shape, you can easily say that this is a forward curve centrifugal fan. So if there is a dip like this, okay, so if there is a dip like this, the meaning of this dip is, you look at this, if you reduce the flow rate, so initially the pressure would decrease, static pressure would decrease, but then at a lower capacity, you'll find that the pressure would drop down. So that is the meaning of the dip. Now what does it mean? It means that uh, if you reduce this flow rate, and if there is a sudden drop in the pressure, static pressure, then this might lead to overloading of this fan. So this is a disadvantage. Okay, so there is a dip in pressure at low flow rates. This is a disadvantage, and this is a distinguishing feature of this forward curve centrifugal fan. However, this has an advantage that it requires very low speed for the same capacity and smaller fan for the same duty. Now, it means that if you compare this fan with the backward curve centrifugal fan or the radial blade fan, you would require a lower speed for getting the same capacity. And the requirement, if you want to handle a same duty means flow rate and the pressure, then you would require a smaller fan and hence lower electricity consumption. That is the advantage. Okay, this fan has a lower efficiency as compared to the other type of fans, but that is not much of a problem because this has an advantage of operating at low speeds, and it requires a smaller fan, which makes it very suitable candidate for HVAC type of a system. This sort of centrifugal fan is found in the most of the HVAC systems. The other type of fan is a backward curved centrifugal fan. Okay, so if you compare this, if you want to understand this forward curved centrifugal fan better, just compare these two diagrams and it would be much very clear. You see that the tip of the forward curved centrifugal fan, it is tilting towards the direction of the rotation. So here I have shown clockwise rotating fan. Both these fans are clockwise rotating, and the rotation is clockwise, and the blade you see this are tilted towards the direction of rotation, whereas in the backward curved fan you'll find that they are tilted away from the direction of rotation. Okay, they are tilted backwards. That is why it is called as a backward curved centrifugal fan. So the forward curved centrifugal fan it would eject the air. The air is ejected radially in the tangential direction, as was explained earlier, from the circumference of the fan. Whereas if you compare it with the backward curve, you will find that this is the direction of ejection of the air. Okay. Let us look at the backward curved fan more closely. This is how it would look. Look at the curves, the veins or the blades, and you'll find that they are backward curved. Okay, and this schematic would also explain why it is a backward curve centrifugal fan. The characteristic curve of a backward curve fan is quite different from the forward curved fans. Okay, so I explained you this kind of curve. This was a typical head curve or pressure curve with respect to flow, where there was a dip for forward curved vanes, but for a backward curved vanes there is no such dip. Okay, and the backward curved centrifugal fan, if you want to distinguish it and if you want to look at this fan just by physical examination, then it would have a cylindrical shape. The blades are largely curved, and then there is a conical inlet nozzle. Okay, and if you want to look at the characteristic curve and identify whether it is a forward curve fan or backward curve fan, then if there is no dip, then you would say that it is not a forward curve fan. Okay, so this is how one can look at the backward curve fan. Now, what is the advantage of not having a dip? The advantage of not having a dip is that if you go on reducing the flow rate, the head would increase. Okay, and if you go on increasing the flow rate, the head would decrease, and this makes it a very stable kind of operation. So with reducing flow, the head increases. With increasing the flow, the head would decrease. Okay, so the power requirement characteristic peaks at high capacities, so the motor does not get overloaded if this fan is selected properly, and that makes it a very stable kind of fan. Okay, this is the most efficient fan and it runs quietly. The pressure curve is steeper, as I said, and it gives you more stable delivery, and as efficiency peak is to the right of static pressure peak, a built-in pressure reserve is available for efficient fan. The other type of fan blade I mentioned was aerofoil blade fan. These are aerodynamically shaped blades, so they give you higher efficiency, but they are costlier. Okay, and hence generally when you are talking about low capacities, you will go for forward curved vanes, and if you are talking about high capacities or moderate capacities, you will go for backward curved vanes. In special applications, one might go for aerofoil blade fans also. Okay, so this is the overview of the description of the fans. Now, what is important for us to understand is the choice of fan or selection of the fan. And the fan is selected on the basis of three parameters. One is the flow rate or discharge, which is Q. The other is the static pressure, because if the static pressure build-up is sufficient, then and then the pressure drop can be overcome. Okay, we talked about FTP, and if the FTP, the pressure fan total pressure, is basically the pressure which overcomes the pressure drop in the ducting system and in the air handling unit. So this is the second parameter which is important, the static pressure built up in the fan or FTP. And third is the horsepower required to get the required discharge and the static pressure. That is the brake horsepower, okay, or the power requirement, power input. Okay, so these three are the important parameters on which the fan is selected, and these parameters, they do vary with the diameter of the fan impeller, and they do vary with the speed of the fan. So the laws governing these different parameters, that is the CFM or flow rate, the speed, that is RPM, the static pressure, that is SP, and the power input, that is brake horsepower, PHP, these are summarized in the fan laws. So these are the three important fan laws. One is relating the flow rate, that is CFM, with the speed. What it says is that the airflow delivered by the fan, it is directly proportional to the change in the rotational speed. Okay, so CFM means it is the flow rate. Okay, cubic feet. This RPM is the speed revolutions per minute. Okay, cubic feet per minute, revolutions per minute. SP is the static pressure. Fan law 2 talks about static pressure developed by the fan. It varies with the square of the change in its rotational speed. Okay, so this is, it varies with the square. Here it does not vary with the square, it is simply directly proportional to speed. And third is very important, that it varies with the cube of the change of the rotational speed. So the power required by a fan varies with the cube of the change in its rotational speed. So these three laws, they are very important in the sense that they talk about three important parameters, that is the flow rate, that is CFM. Then the second parameter I talked about, that is the buildup of the static pressure, SP, and third is the power consumption of the fan. Okay, so understanding this fan laws and using them help us to calculate or predict the performance of the fan under different operating conditions. When we talk about the operating conditions, finally, let us discuss this curves. These are the fan curves and the system curves. Now, what is a fan curve and what is the system curve? If you go to any manufacturer, the manufacturer would supply you this kind of curve. Okay, this is the curve which is shown, which is called as a fan performance curve. It would be either in the tabular form or it could be plotted as a pressure versus volume. Okay, and you find that this fan pressure versus volume curve is parabolic. Okay, and you also find that they would provide you with the efficiency curve. So this is a fan efficiency curve, right? So this means that it shows you the behavior of this fan, right? But fan does not operate in isolation. Fan operates to overcome the system pressure. Now, what is the system pressure? System pressure is the pressure in the duct and in the air handling unit. Okay, so this is a typical system curve. You know that with the flow rate increases, the resistance offered by the system would go on increasing. Okay, so this is what it shows, that if your flow rate increases, the resistance offered by the system increases, and this is the fan curve, which shows a peak and then it reduces. Okay, now if you plot this two, then these two would intersect at a point which is called as a system operating point. Now, what is the meaning of system operating point? The meaning of, when you superimpose these two curves, the intersection, which is the operating point, it tells you that at this fan, when it is delivering this flow rate, that is Q flow rate, then its pressure drop would be this P. Okay, the meaning is, if it is delivering this flow rate, then it is going to overcome this pressure drop. Okay, now let us assume that the ducts are not clean or the filter is not clean. So what would happen to this? How would this curve change? The system curve would go upwards. Okay, so if it was like this, if it was intersecting at A, now if there is some dirt in the filters or in the ducts, then the resistance would increase. It means that the system curve would now rise and it would increase at, it would intersect now at B. It means that initially, if it was a clean duct and the system resistance was less, it would deliver Q1 higher flow rate. But if there is some problem with the or resistance in the air duct, then it would deliver less. So that is how it helps us, this kind of curve helps us to estimate the operating point of the fan duct system. So fan is not to be understood in isolation. It has to be understood in combination with the system, and system means the HVAC duct. Okay. So if in toto, what is the understanding of us after this discussion? We have understood how to select the fan by calculating the fan total pressure. We have understood what are the different types of fans and what type of fan is generally used in the HVAC systems. We have seen the characteristic curves of the two different types of centrifugal fans. One is a forward curve type and other is a backward curve type. And we said that the forward curve vane fan is more commonly used, though it has a disadvantage that there is a dip in the characteristic curve and it is not that stable as compared to the backward type, but it is suitable for the operating conditions which are encountered in the low pressure high volume systems like low pressure low volume systems like HVAC systems. Okay, and then finally we said that there are fan laws which govern the operation of the fans or selection of the fans. We talked about the three fan laws, and finally we talked about system operating point, which is the intersection of the system curve and the fan curve. We said that this system operating point would shift if there is more resistance encountered, and we need to make sure that for efficient operation this system operating point always operate at the best efficiency. So this is the best efficiency point and this is the system operating point. So if this best efficiency and this is point and the system operating point they are closer, your operating cost would be less, the electricity consumed by the fan would be less. Okay, so as engineers we need to be careful about the selection of the fan as well as operation of the fans. Thank you.